In the third module this week, we arrive at a crucial topic: renewable energy variability. We said that wind and solar energy technologies are very cheap. The cost per unit of electricity, the cost per kilowatt hour produced, is low. But the big question mark is variability. If, say, with a solar power plant, half of the day we get cheap electricity, but half of the day we get no electricity at all, how useful is this in fact? You can see here the amount of sunlight hitting the ground throughout the globe estimated by a NASA global weather model. There's obviously the day-night cycle, but there are other things happening too. For example, large dark areas where clouds block sunlight during the day. We need ways to understand and quantify the variability that results from weather patterns like these. Some of this variability is very short-term, a cloud moving across an area temporarily reducing sunlight. Some of it is much longer term, winters being colder, windier, and less sunny than summer. We want to look at two ways in which to quantify this variability: capacity factors in this video and load duration curves later in the exercises. To do so, we'll turn to a concrete example. This is time series data for daily averages of all of Germany's wind generation in 2019. Time series means that the data points are sorted by time. We see that wind generation fluctuates quite dramatically over the course of days and weeks. Certainly it seems like, at least in 2019, there are more windy periods in the colder months, so we see seasonal variability here. And we see that there can be days with very little wind any time of the year. So let's start quantifying this. We start with the capacity factor, or CF. The CF is a way to summarize the time series into a single number. That makes it easy to compare different locations or different technologies. Here is the definition of the CF for a specific period of time. It's the total electricity generation during that time divided by the length of time multiplied by the installed capacity. So let's say that Germany has about 60 gigawatt of installed wind capacity in 2019. We can then sum up this time series over the whole year. Gives us about 123.8 terawatt hours or 123,800 gigawatt hours. And we divide this by 8,760, the number of hours in the year, times 60 gigawatt. That gives us 0.24. So the capacity factor of wind power in Germany in 2019 was 24%. We can do the same for just summer. Say June through August. Summed generation is about 18,900 gigawatt hours. We divide this by 2,184 hours, the number of hours in these 3 months, times 60 gigawatt. And we get a summer capacity factor of 14%. So the intuition that generally the colder part of the year is windier is correct. We see that with a lower capacity factor in summer compared to the average capacity factor of the whole year. How do we work with the capacity factor? Well, let's add German PV generation. The first thing you notice is that the absolute amount of electricity coming out of Germany's PV systems is quite a lot less than that coming out of wind farms. We can calculate the annual capacity factor for PV, same as before, and we get an annual average CF of about 11%. This means that for the same amount of installed generation capacity, German PV produces roughly half of the electricity than German wind power does. What is important is that the absolute level of production doesn't matter for the capacity factor. If Germany doubles its installation of PV systems, the capacity factor will remain roughly the same, unless they build all the new PV systems in unusually sunny parts of the country, then the CF would go up. So the CF is really a number that tells us about variability. And without knowing the installed generation capacity, it tells us nothing about how much electricity we actually get. And it averages out all the fluctuations, like the fact you see here very clearly that PV produces more in summer and wind is the other way around. So the CF has its limitations. and we will discuss this more in the exercises. Still, it's a very useful number because it's so easy to compare across different technologies. Here you can see some typical values for some of the technologies we already mentioned. Now, one thing to note is towards the bottom of the list here. Remember I said that CSP, concentrating solar power, can provide 24 hours of electricity. So if it is always running and producing electricity, shouldn't it have a capacity factor of 100%? Even more, I included nuclear power as well. A nuclear power plant's main strength is that it always runs. So again, why does it have a capacity factor of less than 100%? Well, even always-on power plants have some variability. For example, a plant might need to go offline a couple of weeks for maintenance. So there will be periods where the plant is not producing any electricity at all, and its capacity factor will almost always be less than 100%. Finally, to get back to our table of technologies, we use PV and wind as examples here because they are the most variable. CSP and hydropower are weather dependent too, so they're still variable, while geothermal is not weather dependent at all, and in many ways more like a traditional power plant that you can turn on and off. We will talk a lot more about how to deal with this variability in week 4. And in the exercises, you will learn about and work with an additional metric, the load duration curve.